So Ethainter is a smart contract security analyzer for composite vulnerabilities. Now this is joint work with my colleagues, Lexi Brent, Sivis Laguvardos, Bernard Scholz, and Yanis Smaragdakis. Smart contracts perform general purpose computations. They make state changes to a blockchain. Some effects of these computations involve the transfer of valuable assets between participants in these networks. Now, vulnerabilities in these smart contracts can lead to devastating financial consequences for the stakeholders. Ethainter leverages our programming language technology, that is science, to find vulnerabilities in smart contracts. And where that is not enough, a lot of verbal grease also helps. I won't talk much about the elbow grease today, but feel free to refer to the paper for some salient details about our implementation. Now, some of you may already be familiar with past work for statically finding vulnerabilities in smart contracts. Now, many of these are geared towards shallow bugs, such as the one I'm going to be explaining now. So I'm going to be using an analogy in the rest of the presentation. I'll be talking about rooms, doors, gold, and pirates. Now, the objective of the pirate is to steal gold from the room. Luckily for the pirate, the room has a door, and the door is open. And so the pirate can simply steal the gold. Now, this translates to the code as an analogy, which you see here. It has a function kill with a public qualifier. So this means that anybody can call that function. Inside that function, there's a self-destruct. Self-destruct removes the code associated with the current address and sends the funds of the smart contract to the address which is passed as an argument. And this kind of vulnerability is called an accessible self-destruct. You really do not want to have self-destruct to be accessible because it pays for people to actually call that, and in the near future, perhaps also bots as well. But these kinds of shallow bugs are not usually present in live smart contracts, at least not ones that have a lot of funds. They can be easily spotted by code reviewers. Now, vulnerabilities on well-funded contracts are much more complex. For instance, the notorious parity vulnerability required 2 separate transactions to exploit. And so it escaped the gaze of professional code auditors. Now, as this interaction, which I'm showing here, between the alleged attacker and some members of the community shows, the vulnerability required 1 transaction to initialize the contract's parameters and 1 to steal the funds. Now, finding sophisticated vulnerabilities, and ones which are not easily stumbled upon just by inspecting code, is what Ethainter does. Okay. Now, since anybody can propose transactions, programmers have learned to use custom modifiers. And these are guards to limit the execution of parts of the smart contract. So for instance, here we are checking that the caller is of a specific account. So in other words, people have started to lock their doors. Thus, this code is not vulnerable, right? Because unless you have the private key of the owner address, so the owner address is a public key, unless you have that matching private key, you cannot call that function. However, when you try to statically analyze, even simple code like this, some smart contract analysis frameworks already struggle to understand code patterns like this, and they actually flag this contract with a false positive. However, Ethainter does not do that. But Ethainter not only models guards, but it also models the tainting of guards, such as in this example. So here in this example, we have a locked room. However, there's another room which is unlocked. And inside that room, there is a key. And so a more sophisticated attacker can take the key, open the door, and then take the gold. Now, this translates to the analogy on the right-hand side where we have a function setOwner. And that's a public function because you get a default public qualifier. And so the attacker can set themselves as owner and then call the kill function. This kind of vulnerability is called tainted owner variable. Now, Ethainter's analysis is recursive in nature, and it uses sound program analysis principles. It can therefore find vulnerabilities that need to be executed over several transactions. And these are hard for humans to simply eyeball. Now, finally, Ethereum has storage, and storage persists across multiple transactions. Now, in this analogy, we still have a locked room, and we still have a key. But this key is securely held by the administrator, so we cannot simply steal the key. However, there's another room which contains the name of a beneficiary, and that room is unlocked. What the attacker can do is therefore set themselves as the beneficiary, and when the administrator takes that information with them to the locked room, then they will send that gold to that beneficiary in this analogy. Now, the point is that tainted information can persist over multiple transactions via storage. And it can then be propagated downstream by authorized users, like this administrator here, in places of the code which are inaccessible to the attackers. You see, the attacker can never be able to call the kill function. But the information that the attacker provides is used within the kill function. Now, this vulnerability is called tainted self-destruct. Okay, so alas, let's look at the formalism of the Ethainter analysis. Now, the formalism is over a simplified representation of the code, but it does capture the key elements of our framework, and these are guarding, persistent taint and storage, data structures which are keyed on sender, recursive vulnerabilities, and so on, as we shall see. The bottom half of the screen explains the notation we use in the inference rules. So let's start from the very first rule, which is a very simple rule, so I hope we can agree on it. This one simply says that if we are taking input from a user, and that input goes to X, then X is tainted. Now, the next two rules are data flow rules. These simply say that if we have a variable Y, which flows as an operand to an operation, then the result of that operation is also tainted. Notice that we have two kinds of taints: taint from storage and taint from input. These are treated separately in our models. And that's because taint from input, by default, it will flow to volatile places of the Ethereum virtual machine. So that would either be stack variables or volatile memory. And so by the end of the transaction, that taint is erased automatically. Whereas taint from storage can persist across multiple transactions. So we treat it differently. In fact, the next two rules start to show how this treatment differs. In the first rule, where we have guards, now guard 1, so a guard is like a sanitizer. It is meant to remove taint from a variable in our model. However, if a variable is tainted from storage, then that taint can flow untrammeled through the guard. On the right-hand side, the rule says that if the predicate which is used by the guard to sanitize the input, if that predicate fails to sanitize, most likely it's because it's tainted, then that taint will also flow untrammeled through that guard. Now let's look at the next set of rules. Tainting of storage is handled by these two highlighted rules here. Storage write 1 says that if a local variable f is stored to a storage address t and f is tainted, then the storage location that is pointed by T is also tainted. Storage load is the dual of this rule. Reading tainted storage locations taints the local variable in which this value is read. The last two rules deal with guard predicates failing to sanitize. If tainted information flows to guards, as in the rule on the left-hand side, or guards do not index the current sender, as in the right-hand side, these predicates fail to sanitize. Okay, so we implemented Ethainter using the data log language. More specifically, we used the GHz framework, which is a powerful decompiler. Now, this means that we inherited some of the characteristics of this framework, such as the scalability. And in fact, we could deploy Ethainter across all the smart contracts that have ever been deployed on the Ethereum blockchain. And that's because it is scalable, but we are also able to get all the code that was ever deployed, because all the code is stored on the blockchain. It's stored in a bytecode format, which is a very low-level format, and that's why you need a decompiler like the GHz framework. Okay, so we can see that Ethainter flags a small percentage of the smart contracts, which is a realistic result. And other than accessible self-destruct, tainted self-destruct, and tainted owner variable, there's another vulnerability I want to talk about, and that is tainted delegate call. This is by far the worst kind of vulnerability you can have in your code. That's because a delegate call allows the user to execute arbitrary code from the smart contract. Now, if that delegate call is tainted, the attacker can inject their own code that will be executed, which means that they can not only drain the smart contract of its funds, but they can use the smart contract as a vector to attack other smart contracts which interact with it. So we also tried an experiment where we implemented a tool which can automatically exploit the accessible self-destruct vulnerability. And we were able to destroy 805 smart contracts on the Ropsten test network. Now, this is not a live network, and so the funds which are on the Ropsten test network are not real funds. So unfortunately, I couldn't retire on the spoils, but we got quite a good success rate. We also compared Ethainter across other tools. For instance, the Securify tool is held in high regard by the Ethereum community and is funded by the Ethereum Foundation. And yet we were able to achieve much higher precision than Securify. In fact, the discrepancy was so high that it seemed surprising at first. Now, the way we got this precision figure is it's an approximate figure, because we took 50 warnings, 50 smart contracts that were flagged by each tool. We manually inspected them and saw whether we could actually exploit the smart contracts under some conditions. Yeah. And we also noticed that Securify flags a lot of the contracts for some violation, which is not a realistic result. We also compared Ethainter against Securify 2, which is a much more modern tool, but it's a different beast. It's a source code analysis tool, and in fact, it only supports a subset of Solidity versions, right? Because each version of Solidity has its own, has its own syntax and semantics. And so we could only apply this on a limited subset of contracts. And not only did we get higher precision results, but we also got, found warnings that Securify 2 didn't find. And that's because it's a source code analysis tool, which means that it doesn't analyze inline assembly. And a lot of libraries in complex projects use inline assembly. And so Securify 2.0 didn't find or missed a lot of the tainted delegate code vulnerabilities that we found. We also compared Ethainter against Ether, which is a symbolic execution tool. Now, Ethainter is a very precise tool, but it's also incomplete. What I mean is that it only flags a very small subset of contracts, 463, whereas we flag a lot more. Of course, the good thing about Ethainter is then, as a symbolic execution tool, it can also give you a trace. But it's incomplete, and it also times out on a lot of contracts. So, in conclusion, Ethainter is a very powerful security analysis framework which overpowers a range of state-of-the-art tools built using different techniques, scales to entire blockchain, and has been deployed as a real-time service, contractlibrary.com. So here is Contract Library. It decompiles and analyzes all smart contracts deployed on the Ethereum network and also on other test networks. If you're interested in the results of Ethainter, you can click on Filter by Warning Type and select, for instance, Tainted Owner Variable. You can also search for your own smart contract. I've had a look at this one, and we can see on line 51, on this one, which is flagged for Tainted Owner Variable, that whoever wrote the smart contract commented out the version which checked for the ownership card. And now anyone can transfer ownership to themselves and then call destroy. So thank you very much. I hope to see you next year in person, and enjoy the rest of the LDI.